Hello everybody, I'm Jean-Romain. I'm a PhD student at the University of Strasbourg, and I'm here to talk about a fast convergence routing of the hot potato, something we worked on with Quentin Bramas, Christelle Pelser, and Pascal Mirandol. BGP is a sleepy giant, right? It's a huge protocol in charge of exchanging routes across internet domains and of ranking these routes in order to find the best one to all destinations. The number of routes of entries to rank is pretty huge, 900,000 and growing, so this process is time consuming. But the real issue comes from the fact that this process has to happen often because of the hot potato routing policy. In short, this dictates that the transit traffic should leave the AS as soon as possible, so by going through the gateway which is the closest in terms of IGP distance. This means that an internal event may affect the ranking of the BGP routes because it may change which gateway is the closest to you. So after any internal event, you need to re-rank the BGP routes. These events are frequent, right? So you end up doing this a lot of times. During these slow and numerous processes, the transit traffic may use suboptimal routes or may not even be able to reach the destination at all. And this is what we wanted to prevent. We wanted to prevent BGP traffic from being affected by internal events. Ideally, upon an internal event, the transit traffic should benefit immediately from the new best BGP route without having to wait for the BGP convergence. And the maintenance overhead necessary for this immediate switch to happen when necessary must be limited, not greater than the processes of BGP itself. To achieve this, we designed OPTIC, which allows to do just that. It allows for an immediate and optimal rerouting of the BGP traffic after any internal event with a low maintenance overhead. More precisely, the switch operated by OPTIC is immediate and optimal, meaning that internal events become pretty much hitless for the BGP traffic, because the latter immediately benefits from the new optimal BGP route after the event. OPTIC can handle any single internal event, so any node failure, link failure, or weight change, and the maintenance overhead, the update time of the structures is fairly limited, so once this immediate switch is operated, we can update the structures of OPTIC in a small enough time to be able to anticipate and prepare for the next event. Of course, OPTIC isn't the first of its kind. There are other BGP schemes that aimed at mitigating the impact of hot potato routing on the BGP convergence, the most notorious one being probably PIC, prefix independent convergence. PIC laid some very interesting concepts and ideas, which we are going to an extent to use ourselves. In short, PIC relied on three core ideas. First, it used a hierarchical fib, which allowed it to quickly consider IGP events, IGP changes at the BGP level. In short, if the best IGP path to the gateway changes, with PIC, you can immediately benefit from the new best IGP path to the gateway. In addition, PIC handled gateways themselves a bit differently. Instead of memorizing a single gateway per destination, PIC memorizes two of them. So if the first one fails, you can rely on the second one. And last but not least, PIC used prefix groups. This means that if several prefixes used the same two best gateways, they actually shared the same set in memory. So if you update the set, for example, by saying gateway 1 is reachable, use gateway 2, this update immediately benefits to all the corresponding prefixes. So even though these are some very solid ideas, there are still some cases which PIC cannot efficiently deal with. And some of them can be shown on this example, which looks a bit complicated at first, but I assure you it's pretty simple, and it's the only one we'll need throughout this whole presentation. The PIC memorizes the two best gateways. So the first limitation, which is fairly obvious, is that maybe memorizing only the two best gateways is not enough. For example, here on this network, if A fails, both N1 and N2 become unreachable, and this leaves us with no backup plan. But admittedly, this type of failure of events should not happen in a well-designed network. A single node failure should not make two gateways at once unreachable, except maybe if the network already suffered from successive failures beforehand. But even if we consider less critical and more likely events, for example, the failure of the link between A and C, there are still some issues. Because here, what PIC would do is quickly restore the connectivity to N1 through the new best IGP path, but it does not consider the fact that maybe this event changed what gateway is actually the best gateway because of the hot potato routing policy. And in fact, here N1 is not the best gateway anymore. It's N2 because it's closer to S in terms of IGP distance. And this new best route going through N2 will not be considered until BGP reconverges and PIC updates its sets accordingly. Even more frustrating, if we consider a pretty impactless event, for example, the failure of S to A, you can see here that the distances to the gateway is unaffected and that the connectivity is unaltered. Even then, BGP has to reconverge just in case, and PIC recomputes and reevaluates its sets, even though the set stayed the same. There is no need to recompute it, you can just leave it as is and spare some computation time. This is the type of events we want to deal with a little bit more elegantly with OPTIC. Right? So we still want to be able to perform this optimal and immediate switch to the new best route after an internal event, but after any internal event. And we also want to prevent superfluous computation so that we can restore an optimal forwarding state as quickly as possible. To do this, we will need to also construct backup sets of gateways. But conversely to PIC, we want ours to be a little more complete, a little more resilient, because we want to be able to state that whatever the event that may happen, the new best gateway is within this set. So the first step is how can we construct such sets efficiently. To explain this, I will need to delve a little bit more on how BGP ranks its route. So BGP routes are characterized by a vector of attributes, and then they are ranked lexicographically according to these attributes. The first attributes, the most important ones, are purely interdomain related. So it's the local preference, the IS path length, the MED, which I'm not going to bother you with during this presentation. These are purely interdomain related. And then later on, you have some intradomain attributes, the IGP distance towards the gateway that announced the route, but this one is less important. The interesting thing to note is that interdomain attributes, the most important ones, stay stable upon IGP events. Right? So if there is an IGP event, they are left untouched. This means that the gateways with the best interdomain attributes before an event will still have the best interdomain attributes after an event. And since these are the most important ones, it also means that the next best route after an internal event is among the ones with the current best interdomain attributes, if there are enough of them, right? Because they do not change. The interdomain attributes do not change. This means that we can actually easily recompute backup sets of gateway. We rank the routes according to their interdomain attributes in a prefix tree. Right? So a BGP update simply means go down the prefix tree, put the gateway or the route where it belongs, and if there is a BGP withdraw, you go down the tree and you remove the corresponding route. In the end, you're left with a prefix tree whose leaves contain a set of gateway share the same interdomain attributes, and the leftmost leaf, here in orange, contains the gateways which have the best interdomain attributes. And we can safely say, for example, in this network, that whatever the IGP change that may happen, the new best gateway is one of these three, one of the gateways in the leftmost leaf, because N1, N4 and N5 cannot become more preferred because the interdomain attributes cannot change. Now, of course, we cannot always rely on the first leaf solely, right? Maybe this leaf only contains one gateway, maybe a single failure may render all of the gateway unreachable. In this case, you need to add more leaf to be safer. What we do in the paper is that we add leaves up until the gateways enable two disjoint paths to destination. So then we are sure, then whatever the event, it cannot render all of the gateways of the set unreachable. If you feel like that's overkill, you can do a little less, it's tunable, but we felt like it's a nice compromise. Now that we have this backup set, we put it within the data plane. And here, all the prefixes that use the same backup sets actually point toward the same set memory. So that if we update the set, it benefits to all the corresponding prefixes at once. So here, for example, let's say that A fails. Then we simply go to the backup set and try to find within this set which gateway is the new best BGP gateway, because we know by construction that it's one of these. The only attribute that may have changed is the IGP distance, so we only need to check within these gateways which is the one with the lowest IGP distance. Here it's N3, so we updated the set so that prefixes actually use N3 now, and once this is performed, the connectivity is restored optimally for all the prefixes. Once you do this for each set, the connectivity is restored optimally for all the destinations. So a single mean search among these sets is enough to restore the connectivity optimally. Now you may have noticed here that even though we restore the connectivity optimally, this set is pretty much done for, right? We cannot rely on it anymore for another event because two of the three gateways became unreachable. So we need to update it so that we can actually use it for a future event. It is worth noticing here that we need to have to update the set because this failure was especially critical, right? Because A is a bottleneck within this network. For nearly any other event on this network, we would not have needed to update these sets. But since this network is not very resilient and the failure is very critical here, we need to update it. So let's see how we do it. Updating the sets is actually pretty straightforward. Once you have gone through the sets to find the new best gateway and restored the connectivity optimally to the prefix, you need to check that if the set is still reliable enough. Can you still rely on it for the next event? If you can, there is nothing to do. But if you can't, then you need to update it. In this case, you simply go back to the prefix tree, which is now updated, and you reconstruct the set. Once you reconstruct it according to your construction condition, you put it back within the data plane, perform the necessary adjustments, if any, and you're done. Your set has been updated. Now, I insisted a lot on the fact that you don't always need to do this, and this is because we expect these sets to stay stable after most events. Right? For example, if we take the condition we use in the paper, meaning that the sets need to enable two disjoint paths to the destination, we only need to recompute the sets if the network gains or loses its biconnected property. For any other events, there is nothing to do regarding the sets. So if you start with a very resilient, strongly connected network, you need to suffer several successive failures without any recoveries in between before reaching a state where events actually means that you need to recompute the sets. Before this, uh, if you don't suffer too many failures at once, or if you can recover from this failure in between, the sets will probably not move at all, which is one of the strengths of OPTIC, is that the backup sets are not computed and not updated after any single event. But even if we do not really need to update these sets a lot of times, we still need to go through them to find the new optimal gateway after an IGP change. So our reaction time or performance is still dictated in a way by the number of sets and their size. So to assess the viability of our solution, we performed an analytical evaluation to predict how many sets OPTIC will end up having to manage in realistic scenarios. To do this, we considered a model where an AS learns 800,000 prefixes announced by p equal 5 gateways, chosen randomly within all the biconnected gateways of the AS, whose number depends on the scenarios we evaluate. The attributes of the routes were characterized by a random integer between 5. These are numbers that were extracted from a published study regarding BGP measurements. Performing this analysis analytically allowed us to easily explore many different scenarios and by easily tuning the number of clients, peers, and providers and how many prefixes they announced. So I extracted some of these scenarios for this presentation in the table here. You may notice that the numbers are a bit different from the one you will see in the paper. This is because we made a small mistake that we corrected. If you want more detail than that, I invite you to go to the website I put at the bottom of the page. The gist of it is that for most cases, for any cases actually, the number of sets that OPTIC has to manage is drastically reduced compared to the number of entries of vanilla BGP. More precisely, for small networks, stub ASs, the number of sets OPTIC has to manage is fairly far from what a lower bound would achieve. So a lower bound is a solution such as PIC, but the number of sets in itself is still pretty small. When you move up to bigger networks, the number of sets to manage by OPTIC grows accordingly, but it actually becomes closer and closer to the lower bound. So it looks like PIC has either is either pretty far from the lower bound but has very few sets to maintain, or has quite a lot more sets to maintain, but it's very close to the lower bound. And in all cases, it's drastically reduced compared to the number of vanilla BGP. So what did we see? We see that IGP events trigger slow BGP convergence, but that we can actually construct backup sets of gateway to handle these IGP events without having to predict and consider each event individually. These sets can be maintained efficiently if needed, but most of the time we expect them to stay stable, and the number and size of this set is limited, which is very promising regarding the performance of OPTIC in more realistic environments, which is why we are now developing a proof of concept using free-range routing to assess OPTIC's performance in realistic environments. And this will also enable us to investigate different optimization, different type of data plane and control plane interaction, and also how OPTIC behaves in more realistic and more diverse IBGP topologies. But overall, we are pretty confident that OPTIC will indeed enable immediate and optimal rerouting of BGP traffic after any internal event for a low maintenance overhead. Thank you very much.